Let us continue our discussion on machine learning for image processing video lectures. In the previous video lecture, we have discussed about the mathematical basics of probability and random variables. We also discussed about joint densities or joint mass functions when there are more than one random variable involved. In this lecture, let us discuss a particular case study of probability density function that's well known or widely used probability density function, Gaussian distribution function or Gaussian density function. So many of the real data can be modeled using Gaussian distribution or Gaussian density. And it is quite common that it is modeled with Gaussian because of its mathematical simplicity and elegance. Let me share the screen. Okay, now let us continue our discussion with a specific example of the probability density function, that is Gaussian density function or Gaussian distribution function. So let us consider the continuous random variable for ease of writing and understanding. So as we discussed in a case of tossing a coin or throwing a die, we have seen that the probability density function usually that occurs is modeled as uniform. So it may be so in case if it is a discrete random variable, we between A and B is the uniform density function or uniform distribution function that will happen, and the height is like 1 by B minus A roughly. So now if we consider it as a continuous density function, a continuous random variable, X as a continuous random variable, then the uniform density function can be sketched as continuous between A and B, and being height being B by A, B minus A. Okay, B where B is assumed to be greater than A. Okay, and this also follows the laws of probability density function, that is integral of P of X is the dx equal to 1 from minus infinity to infinity, and here it is essentially A to B, and P of X is always greater than or equal to 0. Okay, so the discrete probability mass function, this for the uniform density we have seen before. Okay, so and this is the continuous counterpart of it. Now the other, this is uniform distribution, uniform density here. Okay, X being uniform random variable. So usually what we do is X we say is uniform random variable. So X is denoted like this. Sorry. X is uniform random variable and P of X is shown like this. So P of X has a specific expression, that is 1 by B minus A for X less than or equal to A less than or equal to B. Okay, so one of them can be just the less than or equal. Okay, fine. So, and then this is the probability density function for uniform density. Another probability density function that is widely used for modeling many of the real situations is Gaussian density. Okay, in this case, if we say that X is Gaussian distributed, normal distribution people call, the other name for Gaussian distribution is normal density or normal distribution. Okay, so X is normal with usually Gaussian density. The specialty of the Gaussian density is that it can be parameterized with mean and variance. It can be completely specified by mean mu and variance sigma square. Okay, so it means that if we are able to give the mean and variance of a normal density, we will be able to exactly sketch it, and we will be able to tell what are all the probabilities for various values of X, for all the values of X in fact. Okay, that's the speciality about this density, and that's the reason why it is mathematically well tractable and people widely use. And many of the natural phenomena also follow this Gaussian density, and hence it is widely, its applicability is even more important. See, the shape of this Gaussian density looks like this. P of x, mathematically, if I want to write, root 2 pi into sigma e power minus half x minus mu whole square by sigma square. As I discussed in some of the previous classes, the Gaussian density usually peaks at the center and then drops down, okay, and then gradually dies down. Okay, so it goes to 0 at plus infinity and minus infinity. So though the Gaussian density goes to completely to 0 only at minus infinity or plus infinity, its energy most of the times is concentrated in within the 3 sigma region either side. Say if we assume this is as a sigma, okay, the standard deviation of a Gaussian density. So sigma is referred to as standard deviation, okay, of a Gaussian density. Okay, so if this is sigma, then this is 2 sigma. Okay, up to here, assume that. Let me mark with another color. This is 2 sigma, and then the 3 sigma, let it be with even different color. 3 sigma, okay, minus 3 sigma to plus 3 sigma. Okay, this axis is what? This is with respect x. X is a random variable that takes any of the values on this line, and the frequency with which it takes the values of x is p of x. Okay, that is the PDF. So if we model this time the student come to the class, then the time is a random variable that is on x-axis. The number of students who come at that time is the probability density function. Okay, that is roughly Gaussian, and it is p of x. It can be modeled with p of x. Okay, so this is the 1 sigma region. Okay, so it's on either side. So this term is referred to as mu. Okay, so and hence this is mu minus sigma. So if we see this interval, mu minus sigma to mu plus sigma. Okay, this is the range. So what is speciality about this Gaussian density or distribution is that the probability that, so if we see probability that x takes a value between mu minus sigma to mu plus sigma. Most of the energy is in fact concentrated from mu minus sigma to x, the random variable x, okay, taking mu plus sigma. Okay, and this is roughly is equal to close to equal to 66% of energy is within this. So if I normalize this such that the area under this is 1, in fact, this probability density function is defined like that. Please note that. So if I find out here, okay, the integral of p of x, okay, dx is equal to 1. Okay, note. In this case, for this, p of x dx is equal to 1. This is the written in that way. And it has, you can substitute mu equal to 0, and then you can see that at mu equal to 0, it is it's the maximum. Okay, if you move on either side, it exponentially dies down. Okay, so that you can observe from this expression as well as from this plot. Okay, so now let us see the other region, 2 sigma region. Now if you consider, so probability that, okay, mu minus 2 sigma to x taking the values mu plus 2 sigma is close to 96% or 97%. Okay, and then the probability that x takes mu minus 3 sigma to x mu plus 3 sigma, Okay, you can consider capital X as the random variable and small x is an instance of the value it takes. Okay, so it is fine to write this as capital X as well. Okay, it's close to 99 point some percent, 6% or so. Okay, it's not close to almost 99 points. So even though it is not very pictorially clear here, the 3 sigma is I have tentatively drawn, but within the minus 3 sigma to 3 sigma range, you see almost all the energy of the this PDF is concentrated. Okay, or most of the times the value occurrence of this random variable is minus 3 sigma to plus 3 sigma values on the on this axis. Okay, mu minus 3 sigma to mu plus 3 sigma. Okay, so now as a very trivial example, wherein if I want to sketch a normal density, this is referred to as normal density with, okay, mu and sigma square, variance sigma square, and standard deviation is sigma. Please note that. And the mu is the mean. So mu gives anyway the mean value, and sigma gives the this spread around the mean value. As you know, mu higher, the spread will be higher, and Gaussian will be a flat Gaussian. Okay, more flat. So if I say that it is normal with, say, this is a referred to as standard normal distribution. And this standard normal distribution, so if I want to, if I mathematically sketch it, okay, it will be 1 by root 2 pi. Mathematically write it, it will be 1 by root 2 pi e power minus half. So what should I write? Let me use a different color for better clarity here. It will be is equal to 1 by root 2 pi. Here sigma equal to 1, mu equal to 0, that's all. So e power minus half x square by x square by 1, okay, or x square by 2. Even simply you can write this as, okay, x square by 2. Okay, this is standard normal distribution. Okay, so whenever we write for a standard normal distribution, probability of x, so or the PDF is defined as 1 by root 2 pi e power minus x square by 2. Okay, so whenever we want to do any computations on this Gaussian density, especially the integrals, we use this standard normal distribution to do that. Say, for example, if you want to know for what is the integral from mu to infinity, okay, that you can see that it is half. Similarly, mu to minus infinity is also half, or any region in this PDF can be integrated using the help of the tables that are available for the integrals that are on the standard normal distribution. Okay, fine. So this is about the univariate Gaussian density, because see here we are using one random variable or one, say, one random variable or one dimension of one feature value. So in the classification terminology, we are collecting only one feature and plotting the histogram that may be close to this normal distribution. Okay, then we say that that feature is having a normal distribution with some mean and variance. Okay, that is a bet, like that can be fitted well with some density, normal density of mu and sigma square. Okay, so this is referred to as univariate normal density. Okay, so let's move on to discussion on, say, what univariate normal. Univariate means we extracted only one feature. Okay, so measured PDF, okay, with respect to single feature or random variable. Okay, So now let us also understand, in most of the cases, as we discussed in the previous class, we will have the, we will not have univariate cases. We will have the multivariate cases. That is, we will have more than one feature that are collected x1 to xd. Okay, and hence more random variables, and hence multivariate random Gaussian distribution. Understanding about the multivariate Gaussian distribution is of great importance for us. Or normal density. Okay. See, if we want more features or more random variables, with respect to that, if you want to write the PDF, so how do we write? We need to write the joint PDF now. P of x1, x2, and so on up to xt, right? And in this case, now, see, if we assume that these features are independent, then we can write P of x1 into P of x2 and so on into P of xd. This simplifies our computations or calculations. Let us first write the multivariate Gaussian density in the case where features are independent. Or the random variables modeled by features are independent. So in this case, we will write first, and then we will also see subsequently in the general case, how does the multivariate Gaussian density looks like. Because in this case, we can easily write, because we know how to write the univariate Gaussian density. So we can extend that to write the multivariate Gaussian density here. So how do we write? P of x1 comma x2, let us aim for writing xt. Okay, so I will expand each of them 1 by root 2 pi. So let me write sigma 1 for the features variance of in feature or random variable 1. Okay, so it is e power minus half. X minus mu 1 may be the mean of features x1. Okay, of for several samples. Please note here that mu 1 is the mean when I take x1 sample. Okay, x1 sample of several x1 feature of several samples. Okay, so in other words, what this one is the, okay, this one is the, okay, feature index or random variable index. Okay, but to get mu1, what I use is mu1 is obtained by statistical average. This is referred to as statistical average. Average or expectation over several samples. Okay, over x1 for several samples. Okay, for the for x1 feature over several samples for x1 feature. Okay, for x1 feature in all of them. Similarly, mu2, sigma 1 is the spread or the variance of x1 feature over again several samples. Okay, okay, so now let us complete this expression. We have written 1 by root 2 pi this into what will happen, 1 by root 2 pi sigma 2. Similarly, sigma 2 is on x2 feature. Okay, e power minus half x minus mu1 mu2 whole square by sigma 2 square. Okay, and so on up to what will it go? 1 by root 2 pi sigma d e power minus half x minus mu d whole square by sigma d square. Okay, so the product of all these univariate Gaussian densities will now give us the multivariate Gaussian density. Is there any mistake here? The answer is yes, because this is measured with respect to random variable x1 only. Okay, x1, please note that it is only a feature or a single random variable. x1 to xd all are different random variables. Please note that. Okay, x1, x2 and xd are d random variables. Okay, please note that. Okay, so d features in general in our application, but these are d random variables. Okay, when we discuss about multivariate. Okay, so when we discuss about multivariate Gaussian density, this all is the discussion. Okay, so now let us simplify this or to give a better look. So P of, so let me write capital X just to make this notation simple, and 1 by 2 pi power how much will be there? So 2 pi power d by 2, because d times I'm multiplying root 2 pi into sigma 1, sigma 2 up to sigma d. Please note that. Okay, because we have here we have here d different features measured or d different random variables, and then the standard deviation of all d will get multiplied, and e power minus half. Okay, let me write in a simplified way, x1 minus mu1 whole square by sigma 1 square plus x2 minus mu2 whole square. What I'm doing now? Sigma 2 square and so on. Exponents, I am bringing the common exponent and then adding all of the exponents. So e power I am just writing only once, and xd minus mu d whole square by sigma d square. Okay, so this whole together is what? This is a special case of multivariate normal density. I'm saying special case because this is the case where the features are independent. Please note that features are independent. Okay, so in that case we are writing all this. Okay, so we'll see a general, even more general case where features are not independent now. So, but let us first complete or simplify this. The multivariate density with random variables or features. All random variables or features independent is, okay, let me write the simplified version here. P of x is equal to, in fact, this is P of x1 comma x2 comma xd. Okay, please note that is equal to 1 by 2 pi whole power d by 2. Let me write pi I equal to 1 to d sigma I. Okay, please note I have even written in a more simplified notation now. Okay, the same thing I am writing in a better, more simplified notation. 1 to d. Okay, so fine. This looks reasonably fine. Okay, looks simpler compared to the whatever bigger expression we have. And let us see this, but this is not the definition in general for multivariate Gaussian density. Now let me define, okay, the multivariate Gaussian density. Definition: variate Gaussian density. Okay, so this is P of, let me write multivariate, right? So it has this. See, x may be now this x1 again xt. Okay, please note that I will write x bar just to make this explicitly look like a vector. Okay, so x bar I will write, and this is no independence is assumed here. Okay, in general, I make no assumptions about the uh, mm, covariances between the features or random variables. X1, X2 may be correlated as well. Okay, or their covariance need not be zero. So in that case, the covariance matrix cannot be reduced, okay, to a diagonal matrix. Okay, because we have seen that in the previous discussions, the two-dimensional covariance matrix sigma 1, sorry, sigma square 1 square, sigma 1 2, sigma 2 1, sigma 1 2 square. This is the covariance matrix for features x1 comma x2. Okay, when we have two dimensions, this is what is the covariance matrix. Okay, and this also we have seen that if when the features are independent, okay, so sigma is equal to simplifies to sigma 1 square 0 0 sigma 2 square for x1 comma x2 being independent. Okay, independent, or covariance of x1 comma x2 is equal to 0. Okay, we have seen that in that case, covariance is 0. This implies that, okay, either sigma 1 2 is equal to 0 or sigma 2 1 is also equal to 0. Okay, that's what we have seen. But this is a special case. In this case, okay, whatever we have written is fine. But now we are trying to write in general case, and hence I have to consider the covariance matrix as such into the picture. Similarly, similar to the mean I have considered. I cannot take the individual elements of the covariance matrix and write this, okay, write this general expression. So what I write now is 1 by 2 pi whole power d by 2 whole power half. Okay. Okay, and then e power minus half. See, the expression of multivariate Gaussian density also looks like univariate Gaussian density. In the univariate Gaussian density, if you see x minus mu whole square by sigma square, essentially what we are doing, this exponential term is measuring a normalized distance with respect to the mean for each of the random variable. And here it is usually referred to as the x minus mu by sigma is referred to as Mahalanobis distance. Mahalanobis distance. And that is what is measured in the exponent. So essentially, the probability is inversely proportional to the Mahalanobis distance. Higher the distance of a random variable with respect to the normalized distance of a random variable with respect to the mean, then its probability is lower. Or it's closer to the mean, the random variable value occurs, then its probability is higher. Okay. So that's what is this normalized distance or the Mahalanobis distance indicate. In this similar manner, we should have some distance measure here as well that will indicate the closeness of the sample with respect to the mean. Okay, and that reflecting the probability. That's what exactly happened. X minus mu. So all are vectors now. Okay, into sigma inverse into x minus mu. This is finally this becomes a single value in the exponent because probability is a single value, and hence it's a scalar. So x minus mu transpose into sigma inverse into x minus again a scalar. Please note that here sigma is what? Sigma is covariance matrix. Are even 3 dimensions. Okay, covariance matrix. Please note that it is a covariance matrix. Okay, how is this defined? If you remember, expectation of x minus mu into x minus mu transpose. Okay, what is its dimension? If the dimension of this is d cross 1, okay, then let me write all the dimensions in different color for better capturing of the details. Okay, if this is d cross 1, and then the dimension of this will be d cross 1 into 1 cross d, so outer product, and hence it is d cross d. And what do you think is the dimension of this? This is, say, please note that here covariance matrix is this, and then the Mahalanobis distance, a vector Mahalanobis distance here is using the vector feature, the Mahalanobis distance here is x bar minus mu bar transpose into sigma inverse into x minus mu, x bar minus mu bar. What is this dimension? So its dimension again is 1 cross d into d cross d into d cross 1. So and hence the dimension is 1 cross 1. It is a scalar. Please note that. This is again whatever we are writing here is Mahalanobis distance. Okay. So it's again a like standard deviation or the variance normalized distance of the random variable from the mean. Okay. By definition, Mahalanobis distance is a standard deviation normalized or variance normalized distance, spread normalized distance of the random variable from the mean. And this is the Gaussian distribution overall. Okay. So let me put the same color. Okay, this is multivariate Gaussian distribution in general. Okay, this is very, very important expression which we will be using all through, and it is very important to understand this expression also to like correlate with univariate normal density. Okay, so let's see now. This is the expression 1 here. Okay, you have two expressions here. Okay, this is one expression. Okay, expression 1. Okay, and this is expression 2. Now the question is there any relation between whatever we have got in the independent case and whatever we have got in the general case? There should be. And the relation, how do we get, is simply substituting. So how do I get 1 from 2? Simply by substituting. Capital sigma is being diagonal values with variances, individual variances, and 0 the diagonal matrix with individual variances. Okay, in expression 2 you will get the expression 1. Let's make a quick check. I will only give a very outline of this discussion. I request you people to go and substitute and verify this completely. So what I have said is multivariate general expression is P of x. Okay, multivariate Gaussian density. Okay, in general, P of x is equal to 1 by 2 pi whole power d by 2 mod whole power half e power minus half. Okay, x minus mu transpose into sigma inverse into x minus mu. Please note that this becomes a scalar to get a probability also being a scalar. Now what we said is the sigma for, say, now let us case this is general case. Expression 2, general case. Now let x1, x2 and so on xd be independent. Once these become independent, how do I write this sigma? This sigma is equal to, see what does it mean? The independent means there is no covariance between x1, x2, x1, xd and so on. See, when we write a general sigma, this is sigma 1 square, sigma 2 square. I am writing in d dimension, sigma d square. This sigma 1 2, sigma 1 3, okay, and so on, sigma 1 d. Similarly, sigma 2 3 and so on, sigma 2 d. Similarly, here sigma 2 1. Okay, so here it's similarly sigma d1 and then sigma d square. So what will happen in this is sigma d2. Okay, what will happen in independent case? This is general. Whatever I have written here is general. Independent imply now features imply sigma is equal to what? It's purely diagonal because all covariances, no feature depends upon the other feature or their correlation is zero. Okay, and then independent or uncorrelated features. In fact, it is not necessary to constrain them x1, x2, x3 as independent. It is good enough to constrain them as uncorrelated features. Okay, so then sigma d square and 0 here, 0 here. Okay, so it's a weaker constraint is also sufficient to get only the second movement, that is the variance term being diagonal, variance matrix, covariance matrix looking diagonal. Please note that this is the covariance matrix of X. Okay, so now let us substitute this into and see what we get. So let us substitute. Okay, diagonal sigma into. Okay, so what do you think we will get? So first let us compute the inverse, sigma inverse and sigma, like determinant of sigma and so on, and then finally substitute it. Okay, determinant of this if we compute, what is determinant of this? So diagonal matrix determinant is simply sigma 1 square, sigma 2 square, okay, and then sigma d square. Okay, so now this implies that determinant power half is simply, okay, sigma 1, sigma 2 and so on, sigma d, which is equal to pi I equal to 1 to d sigma d. Please note that. Okay, which we had seen in the denominator of the expression 1. Okay, so now let us move on to the computation of sigma inverse. What is sigma inverse? Sigma inverse, any diagonal matrix inverse is inverse of their elements, diagonal elements. Sigma 1 square, sigma 2 square, and so on 1 by sigma d square. Okay, because the other elements are 0. Okay, you can consider this as like a diagonal matrix. Inverse is simply inverse of diagonal elements. Okay, and then this is this when we let us compute before we directly go and substitute, let us compute the Mahalanobis distance first. Okay, let us write, sorry, previously I have to write Mahalanobis distance square here. Okay, so because it is the square of the Mahalanobis distance what we have written here. Okay, please note that here there is no square required because x minus mu by sigma only I have written. Okay, so but this is the square of the Mahalanobis distance. So now bringing the Mahalanobis distance square, x minus mu. Okay, so let us expand this for simplicity. X1 minus mu1. Okay, I am writing the transpose I have to write. So let me write x1 minus mu1. Okay, x2 minus mu2 and so on up to xd minus mu d. Okay, and this is one vector, that is x minus mu or transpose, and then I have to write the sigma inverse. Please note that sigma inverse is, okay, 1 by sigma 1 square, 1 by sigma 2 square and so on 1 by sigma d square. Okay, sigma inverse. And what should I write here? x1 minus mu1, x2 minus mu2 and so on xd minus mu d. Okay, so if I do this operation, what do you think I will get? X1 minus mu1 whole square by sigma 1 square plus x2 minus mu2 whole square by sigma 2 square and so on. So I will write here for completeness, and then x1 minus mu1 whole square by sigma 1 square plus x2 minus mu2 whole square by sigma 2 square plus and so on xd minus mu d whole square by sigma d square. Okay, So this is what I get as the Mahalanobis distance. Now let us bring back these components and then let us substitute in expression 2 to complete the proof, indicating that the independent case, whichever we have considered before, has exactly resulted in same. 2 pi whole power d by 2 pi I equal to 1 to d sigma I e power minus half x1 summation xi minus mu I whole square by sigma I square. I equal to 1 to d. Okay, this is exactly equal to expression 1. Okay, so on substitution, Gaussian of okay more and in 1. Okay, in 1 results in 2, sorry, in 2 results in 1. Okay, please note that this is the multivariate distribution or density function for the multivariate for the features being independent, when the features are independent or uncorrelated. Otherwise, we should have a general expression. But in general, p of x, we should remember that, okay, it is 1 by 2 pi whole power d by 2 half minus half x minus mu transpose sigma, and sometimes bar also may be left. Okay, for in general, okay, multivariate Gaussian distribution is this. Okay, and please note that mu and sigma, that is mean vector and covariance matrix of multivariate random variable, multivariate random vector. Okay, determines the Gaussian density. Completely determines the density. Okay, please note, make a note of it. So if how usually we denote a multivariate Gaussian distribution is equal to n, okay, mu bar comma sigma. Okay, this is how we denote a multivariate Gaussian density. So to conclude this discussion, I will give you some samples. Okay, and say I will give you some two-dimensional samples now. So first let me give some one-dimensional samples. X takes the values, following values. Yeah, these are all the possible values X has taken. Okay, and compute mu and sigma square given realize or of instance values of random variable X. Okay, so I have given a six instances of X, okay, which the random variable has taken, and from that compute the mean and variance. What is the here I have not given any probability density or probabilities. So the mean expression is simply, okay, if xi are the possible values, I equal to 1 to n, okay, 1 by n. This is the expression for mean. This is sample mean. referred to as sample mean. Compute mu and sigma square. This mu is sample mean. That is sample mean and variances. Okay, here no probability. We assume that it is uniform probability. Each may occur at uniform probabilities. What is the expression for this? Xi minus mu whole square I equal to 1 to n and 1 by n. Okay, these are the sample means and sample variances. Okay, now what I do is I will give two-dimensional samples. Okay, x equal to 0, 0. These are the possible values. 1, 1, 2, 1. Let it be 2, 1 and 1, 2. Okay, assume that these are all I have given. Then compute again sample mean, mu bar and covariance. In two dimensions, we should not call it as variance, we should call it as covariance. Sigma. Covariance matrix sigma. Okay, in fact, it will be a matrix. Okay, covariance matrix sigma. Now compute the sample mean. The expression for sample mean is 1 by n again. Sigma xi. Please note that each is a vector. Okay, I equal to 1 to 3 here, 3 samples. Please note that this is not the index. Okay, x, if you want to differentiate with index, you put it here. Okay, xi being a ith sample. So this is x1, this is x2, and this is x3. Okay, so here please note that this is the index is for the sample index, not the feature index. Okay, so if I within the sample there is a feature index. Okay, so it's a vector. Similarly, covariance matrix also xk minus mu into xk minus mu whole transpose. Take the samples k equal to 1 to 3, 1 by n. Okay, 1 by n. I have written n for generality. Okay, compute them. And then say if we say that with this mean and variance, there is a Gaussian density. How should be the Gaussian density? Just form the, so like relate, right, expression for Gaussian density with this mu and sigma square. Okay, please repeat the same. Write the expression for multivariate Gaussian density with obtain mu bar and sigma covariance matrix. Okay, that this you can do it as an example. Okay, this is exercise 1. And this is 2. Okay, so with this we will conclude this class, and let us now meet on the next class to discuss on the Bayesian classification aspects directly. Thank you.